Hello people, one last little bit here. I'm going to just run through one final possible argument real quick, just to shut down the infinite series or sequence one last time. Let x prime equal even one output of the Collatz. The first output, you have a seed value, x prime equals the next output. Let a equal some value for 2 that let's say this was an even number, you get, or this was, some even number, right? You get an odd, even, so even, but it's not. N is some integer that is now going to be odd, and so is x prime. Let b equal the number of iterations necessary, right? The number of iterations going through, such that b minus 1 is greater than or equal to a. B is always one bit bigger, right? There's always at least one more 3 than there are 2's. So it grows every time. It doesn't dip back down to another value. It can have ups and downs, but there's an average of at least one more b than there is a. If you do some quick analysis of this equation, you'll see that as a it grows with b, as b grows large, this approaches, or should be like this, I guess, 0. And x, or actually I shouldn't do that, it goes different, but x approaches a very small value. X prime has to become a very small value. It can't rise with b. If a stays small, it gets even worse. A has to stay big in order for this, because as these approach infinity, these become incredibly small, but this becomes even more incredibly small. If that's the number of iterations, this will be some odd number, and then this will be the number of iterations later. You can keep going through, and you just add one more time, multiply 3, right? You're essentially the same thing, and then adding one more on top of it. Some odd number times 3, and add one more on top of it, so it's another odd number times 3, until you get some other odd number times 3 times, right? It's essentially the argument I'm making. I know there's some mathematical problems with it, but very few, and it doesn't affect the argument. You'll see. This linear set of solutions, as b gets large, x prime gets small. And this intercept becomes a fractional value. Y becomes a fractional value as b gets large. Or n becomes a fractional value. What is it, like 1/3? Or is it 3b over 2a or something like that? It becomes some like nearly impossible value, right? It's an impossible set of solutions. If the number of iterations grows large, and you keep a as small as possible, right? As few powers of 2 pulled out as possible, x gets small really fast, becomes impossible. It's asymptotic almost to 0. To this being a 0 value. And this becomes a 0 value. It's, these two become small the larger those are. If this stays small and that grows large, this becomes a very small value. And that's what would be required for an infinitely rising series, which would require that this output be getting larger as well. This output would need to be larger and larger and larger and continuing towards infinity as well. But the more iterations you do, And the lower the power of 2, the faster those become impossible to get larger. The quicker they become 0. Well, I shouldn't say this. This goes to infinity, but this becomes 0. I'm speaking wrong. Yes, this goes to infinity, but this becomes 0. And this b does it quicker than a. This does go to infinity, but this has to be closer and closer to 0. This output has to approach 0. X at some point, if this becomes small and this becomes large, X has to be tiny. X has to be tiny. X prime has to be tiny. The blast output has to be tiny. It doesn't grow to infinity. It does a little bit. It's like, oh, how many? You want to say like, oh, this is b times this. This is some odd number. The values it can take as that grows large, right? The output has to grow exponentially. I'm kind of saying the same thing. You're like, but this has to be small. This has to be small to start. In order for this to go to infinity, this has to be small to start. It, in fact, approaches 0. And I think it's like 1. The slope becomes, like it just goes to wicked, it goes off to infinity, but wicked fast. The more iterations it takes to do, the faster that'll have to go. And the solutions to that preclude it running off to infinity. So I hope that makes it a little bit more clear. You'll add that many iterations and it'll be 3 times it that many times. You can worry about the 2's, like how many have to, as long as the number of that is less, right? This can go to infinity, which it does, but it does so quicker the more the b is, which is what you want, but the slower this value has to be low to start. As this goes to more, this value has to be low. It's just kind of, right? It will it will just take off. And you're saying, oh, well, which one? Again, so like I said, yes, there is a solution to this. And you'd be like, hey, this starts to approach infinity fast at lower numbers. You get to high numbers really fast. You plug a number in there, you're like, hey, okay, this approaches infinity. Yes. Integer stuff, you want that. That's the equations that you're saying. That's the special case you say. The infinite set of integer solutions to that equation, so long as that holds true. As n approaches infinity, this value a will stay small. Or will always stay less than b minus 1. I could probably actually take this. Just make it a, because a is already smaller than b. Requires x to be odd. Again, those are iterations, man. It takes off to infinity, all right, but it does it really fast at a low value. Basically says anything can or nothing can. All right, this is essentially 3b, and that's replaced by b divided by 2. Anyway, there's the argument you're trying to make. This is what you're saying is a viable solution set for the runaway odd. That's the solution set for the runaway odd. That's basically what I am hearing. For some x prime that output a number of iterations later, that's what it has to be. That rounds off to infinity, but I believe that those intercept values that you need to get those are fractional. So, anyway, there's that argument, just to throw one more out there. I understand that there's solutions to that, but I believe they're fractional for the odds. Anyway, there's the last of those. Thanks for watching.